Hi everybody, I'm Guillaume Guimbretière. I'm senior researcher at the LACI laboratory of the University of La Réunion, and I will present to you our work on solar cooking at the domestic and artisanal scales. This work is the result of collaboration with Alexandre Lefèvre, Sylvain, Barbot, and Fabrice Laurent from the Eco-Pratique Association. And we thank the organizer for giving us the time for this presentation. Okay, to quickly introduce myself, I have PhD in physics and I have been working since 2019 on alternative technological regimes as part of our world's transition towards more sustainability. And in particular, I'm working on low-tech technology and citizen science. Today, I present to you our first work on solar food processing. Below, you see the outline of the presentation. We'll first talk about generality on the global transition energy in the context of cooking, our definition of cooking, and our scientific approach which seeks to encompass in the same approach to the social and technical issues of solar cooking. Then I will present our first results concerning solar cooking at the domestic scales, and then our community scale solar cooking projects. To start with some preliminaries, so you see here represented the CO2 emission per inhabitant and per year of a French person, and we see that we are currently at around 11 tons of CO2. If you want to go down to the level of the Paris agreements, we have to go down to 2 tons of CO2 here. We therefore need to divide by more 5 our CO2 emission. We also see that the orange and blue emission items relating to food and housing are important items, and that there is therefore an interesting lever in terms of cooking. Why do we cook? We cook for sanitary reasons first, because it destroys pathogens with temperature. We also cook because we improve the energy yield of our food by improving digestion. And finally, we also cook for social reasons, insofar as cooking improves the taste of food, and in most societies, the meal is a moment of strong socialization. I spoke of France. Here, we are on the island of La Réunion. It is a French tropical island which is in the southwest of the Indian Ocean. Rice has a central place in the current food practices. If we calculate the energy consumption dedicated to cooking rice in Réunion, it is equal to 3.1 thousand tons oil equivalent per year. This represents 3% of the domestic energy consumed in Réunion. And that within the framework of a society that functions like the one we currently have. If we project ourselves into a society which will have divided its energy consumption by 5, this would then represent 15% of the total domestic energy, and that only for cooking rice. We see here that cooking is extremely energy intensive. Another reason why we decided to work on cooking is to realize that in a so-called developed country like France, accessing to the energy needed for cooking is currently not a problem. But in a scenario of difficult access to energy, it will become dramatic because cooking is a basic need and this energy need is difficult to contract and it's not negotiable. We are going to work on cooking. So what is our definition of cooking? We have defined cooking as follows. To cook, I mean to follow a recipe, is to ensure that food follows over time a temperature curve that we can simplify to the following curve. We have a heating period, a flat range period, and period of decreasing temperature. All the difficulties and the trick of the cooking will be to succeed in obtaining the curve which corresponds to our objective of food processing. For example, 45 degrees for yogurt making, 65 degrees for starch gelatinization, and 145 degrees for Maillard reaction. We also have two thresholds, an upper threshold above which the food will be burned, and a lower threshold below which the food will not be cooked. How are we going to process food? What we see on this slide is a temperature scale with at the top the biophysical chemical reaction that we seek to obtain, and below the tools that allow us to achieve them. We will not, because I will talk about it later, the electric yogurt maker around 45 degrees, the electric rice cooker around 100 degrees, and the electric bread oven in the highest temperature around 200-300 degrees. The objective here is to obtain a solar tool which make it possible to carry out the reaction which we have seen above. Everyone knows it's there, but I quickly remind you that solar energy does not emit any CO2. Those tools that are often simple and user-friendly to implement. Solar energy is an accessible flow that affects the entire Earth planet. We therefore have a technology that is sustainable, accessible, and easy to implement and maintain. We have a very good example of low tech. Is it difficult to use the sun for heating? Here I represent again a temperature scale with the food processing on the left. In the middle, around 600 degrees, we can melt aluminum and do pyrolysis, and around 1000, 1500, it is the industry of glasses and metals. And we see that in Odeyo, in the Pyrenees, in France, there is a research furnace which is up to 3500 degrees with the sun. If we can reach 3500 degrees with the sun, it is certainly easy to reach lower temperature. This is indeed the case. For a long time, this technology has been mastered. From the 18th century, solar ovens were built. Towards the end of the 19th century, it was so mastered that Augustin Mouchot won the gold medal at the University exhibition in Paris with a prototype solar printer. We see here various recent prototypes of solar cookers. Why solar cookers are not widely used? First of all, we think that it's important to not confuse transition and substitution when we talk about energy transition. Here, we'll analyze the elements that limit the distribution of solar cookers. First of all, solar is a variable resource. Indeed, but we can consider that photovoltaic technology or solar thermal heating for domestic water are widespread, and so it is therefore not because of this reason that there are few solar cookers. It is a performance issue. We have just seen that is not in the slide before because solar cooking has been working for a long time. It is because people are not ready. We see in this study in the so-called developing country that if we look at the criteria for adopting solar cookers, there is an environmental factor first, where if there is no sun, it is difficult to cook. And after that, we see that the cultural factors comes before the technical factor. We are well with a double problem where the technical is linked with the cultural. In fact, we have a problem of efficiency linked to an objective, which is that of cooking. And our main question is how to combine in the same problematic technical and societal approach to innovation. We have two legs for this. We were inspired by the low-tech movement, which is a techno-critical approach that questions for the technological answer to a need expressed by a citizen, and by considering very important, the impact of this technology to the environment and the society. We have also worked in collaboration with citizens to stay in touch with reality in use, and that's why our team is made up of people from research centers and associations. Now I'll introduce you to our work on home-scale food processing. I mean yogurt production and cooking rice. So how are we going to study our solar cookers prototypes? Here we take our definition of cooking with the temperature versus time space, and in it we will measure the temperature TR0, TFR, and TLT. Then we can estimate heating power here, a flat range here, that we will define by its temperature level and its duration, and the negative cooling power. We can also define a standard energy efficiency as well discussed by Khalifa in the 80s. For this, we record the dynamics of solar irradiance and the different temperatures as a diagram. First, we made yogurts. So we start from our needs, following the low-tech approach, and our need is to make 8 yogurts jars for free storage. For storage, they can be prepared at any solar time, and we have to manage a population of ferments around 40-45 degrees during several hours, 6 to 8 hours. We define a high threshold at 68 degrees, where pasteurization kills ferments. And we decide to fix low threshold at 30 degrees, where the population of ferment no longer evolve with the desired balance. Concerning our solar yogurt maker, it consists of a black aluminum pot which serves as a light to heat converter and thermal energy storage materials. It is embedded in a plastic bag to cause a greenhouse effect. There is a temperature probe in the yogurt, a temperature in contact with the pot, and the solar urgence measurement. Below are the parameters of the different materials, mass, and calorific capacities. For yogurt, we took the water one. Then we record the following curves. In yellow, the solar radiance which exceeds 1000 watts per square meter because we are in the tropics. In green, the temperature of the black aluminum cooking pot. And in red, the temperature of the yogurt. We can see the two thresholds, the lower one at 30 degrees and the upper one at 68 degrees. Then we apply the approach presented above. We can estimate the heating power of the pot, which is 17 watt, the heating power of the yogurt, which is 16 watt, the flat range at a temperature of 50 degrees and a duration of 2 hours, a temperature decay of negative power of -4 watt, and we also notice that it stayed 6 hours at the target temperature range between 40 and 50 degrees. Finally, we managed to make yogurt despite a drop in irradiance around noon because of the clouds. We observed that the heating power in the yogurt is equal to that in the pot, which means that the heat transfer between the pot and the yogurt is very efficient. We also notice a loading effect which can be problematic insofar as in the limiting case of a very small quantity of yogurt, you will be heading toward the green curve, like this, which exceeds the upper threshold where the ferment dies. One has to be careful not to have too much power and not enough inertia. We now address our study of cooking rice. Our need is cooking rice ready for the meal for 3 people. We used basmati rice, and here at the top right you can see the different barometers related to our study of rice cooking. The solar cooker on the left is made of aluminum reflector, double glassing, wooden box and crumb paper insulation. It's only recycled materials, and our life cycle analysis is quite simple. It's immediately sustainable from the first cooking. We can define a high threshold of 180 degrees, the Maillard reaction, above which the rice will be burned, and the lower threshold at 65 degrees, which correspond to the starch gelatinization. And below this, the rice will not be cooked. We made the first measurement, like you can see here the results, where the aluminum pot was empty. Over the time range where the energy efficient is 15%, the low threshold is largely exceeded here, and the heating power is 31 watts. About cooking rice. We first made an experiment where the rice was cooked in a 400 electric pot. In red, at left, you can see the rice temperature curve, and in gray, the electrical power consumed. We applied the same analysis as above, and it gives a heating power of 260 watts, a flat range at 100 degrees and for a duration of 10 minutes. And we consumed 384 watts during 24 minutes, and it's equivalent to 0.15 kilowatts of energy consumed. Concerning solar cooking, we do not open the cooker, we just wait until the meal. The cooker is in place from 7 in the morning. The analysis gives a heating power of 14 watts on a flat range at 90 degrees with a duration more than 2 hours. We can observe first that the rice is cooked. It's a success. Power on load is about half of power on no load. The low threshold is crossed after 1 hour and 40 minutes here. This is the minimum cooking time under this condition. And that energy efficiency is not very relevant because the energy loss not consumed is lost in the environment. Regarding cooking on the domestic scale, what are our observations and conclusions? On the threshold consideration, we notice that these thresholds are dependent of the recipe. In the context of yogurt, we have seen that there was a loading effect. If the quantity of yogurt is too low, there is a risk of exceeding the threshold. It is too necessary to find a balance between power and inertia, which raises the question of whether the pot is part of the solar cooker or of the load. In the case of cooking rice, the low threshold is exceeded after 1 hour and 40 minutes. On the power consideration, yogurt maker and rice cooker have the same heating power. The yogurt maker works not only during the heating but also during the flat and cooling range. The heating power of the rice pot is halved with the load for 2 similar days in Réunion. It will be relevant to have a standardization approach based on the work of Funken collaborators and the relevance of energy efficiency. We can surely improve our rice cooker, but it is not essential because we have met the need, that is, obtain cooked rice. It will surely be more interesting to note that the low threshold, close to 65 degrees, is largely exceeded. We rather think of working on low temperature cooking. We also believe that it is not relevant to work on energy efficiency because the unused solar energy is lost anyway. We finally find that cooking is not just a problem of thermodynamics but also of uses. The next part concerns our work on solar cooking at the community level. Why we work at the community level? It is clear that technologies are non-neutral and carry within them a model of society. And we assume that craftsmen are a population that can more easily learn a new gesture and the use of a new tool and therefore carry this model of society. For example, it will be possible to manage energy as a common, in the sense of Elinor Ostrom, and to have a collective management of solar tools. This is a project that we are carrying out in Réunion. We are working on the organization of a network of solar bakers. This project is just starting. To move forward, we connect the spatial distribution map of baker and solar irradiance. In terms of land use planning, we ask ourselves several questions. What are the thresholds of solar viability at different scales, daily for cooking and at the level of the week or month to support a different economic model? Also, it is possible to have light and mobile infrastructure allowing a sharing of land use. When we work at the community level, we have the same approach as at the domestic level. We are working to compare current tools with solar tools with the help of craftsmen. At the top right, you can see the temperature recording in a 48 kilowatt electric baker's oven over several days. We see that the dynamic is much more difficult to analyze than the simple cooking of rice, for example. There are periods of rest, and at the end of this period, the temperature has not returned to ambient one. There are warm-up periods and cooking times. We ask ourselves the same question and are beginning to have some answers. First, the temperature range for cooking is quite high, between 180 and 250 degrees. Traditional cooking is done in falling heat and cooling power may then be a key factor. Below, you can see that we also made some measurements on the 5 kilowatt solar roadster oven model in Lyon, France. And without going into detail, we see the two roasting sequences close to 200 degrees. Now we will conclude. We have seen that the problem of energy for cooking is a fundamental question because cooking is a basic need. Adoption of solar cooking is a socio-technical issue. It is therefore necessary to think of energy at the level of the energy need and the energy service. We also note that our approach centered on the recipe. It means by considering thresholds in time and temperature, this approach is effective. It allows us to validate combination of tools and use. We also efficiently made yogurt and cooked rice with two very low-tech prototypes. We also succeed because we collaborated with citizens and we are very happy with our collaboration with which starts with the craftsman. As outlooks, we can note that in 2022 we will continue to see the same kind of characterization on the craftsman solar prototype. And we are going to explore the cooking of rice as close as possible to the low threshold of starch gelatinization. And thank you for your attention.